All right, let's just dive right into it. Today, we're exploring a paper that, no joke, basically built the foundation for the entire digital age we live in. We're talking about Claude Shannon's landmark 1948 paper, A Mathematical Theory of Communication. It's this incredible piece of work that took super abstract concepts of human interaction and, well, translated them into the hard, undeniable mathematics of information.
So right off the bat, Shannon drops this completely radical premise. He says that when you're engineering a communication system, the actual semantic meaning of the message, it doesn't matter at all. Literally irrelevant. Whether you're transmitting, say, a grocery list, a heartfelt poem, or just a string of completely random numbers, the engineering problem is exactly the same. The system's only job is to accurately reproduce that selected message at its destination. That's the whole shebang.
But, that really begs a massive question. If the meaning doesn't matter, how on earth do we measure information? This right here is the ultimate puzzle that had to be solved to make modern communication, and honestly, modern computing, even possible. Think about it. If we strip away all human emotion and meaning from a message, what exactly is left to measure?
To figure that out, we're going to follow the journey of a message from its creation all the way to its destination. We'll uncover the math behind it in 5 steps: the universal communication problem, measuring information with bits, the structure of language, entropy and message redundancy, and finally, combating channel noise.
Okay, let's jump straight into section 1, the universal communication problem, and really look at that fundamental challenge of perfectly reproducing a selected message at another point. What's so brilliant here is Shannon's macro view. He takes any kind of communication, I'm talking a television broadcast, an old-school telegraph, or even just you and me having a conversation right now, and he abstracts it into this incredibly simple, universal structural flowchart. Because at the end of the day, every system, whether it's discrete, continuous, or some mix of both, breaks down into these 5 essential parts. It always starts with the information source, right? The thing that produces the message. Then, the transmitter encodes that message into a signal that actually works for the channel. And the channel is just the physical medium the signal travels through. From there, the receiver basically works backwards to decode that signal, finally delivering it to its destination. By looking at communication through this superstructural lens, Shannon gave engineers a completely standardized way to evaluate literally any system. An absolute game changer. All right, moving on to section 2, measuring information with bits. Now that we have our universal system, we need a way to actually measure the stuff flowing through it. So Shannon needed a baseline unit, and he ended up adopting a logarithmic measure, specifically base 2. He introduced this concept of the bit, which, fun fact, is actually a clever contraction of binary digit that was suggested by J.W. Tukey. Anyway, he makes the bit the fundamental unit of information. And a bit is just incredibly practical because it maps so perfectly onto physical engineering elements. Think of a relay or a flip-flop circuit. They have exactly 2 stable positions, on or off. Simple as that. To make this a bit more tangible, let's think about how different systems store data. While a simple flip-flop circuit stores 1 bit in base 2, picture a base 10-digit wheel on one of those classic old-school desk computing machines. It has 10 stable positions, right? Mathematically speaking, that digit wheel has a storage capacity of about 3.32 bits. By standardizing this measurement, Shannon basically proved that everything we transmit can be quantified absolutely regardless of what physical device we happen to be using. So let's bring this abstract math into the real world with section 3, the structure of language. How on earth do we handle something as wild and complex as human language? Well, think about it like this. If we just assigned an equal probability to every single letter in the alphabet, we'd get complete zero-order gibberish, just total randomness. But human language doesn't work like that at all. By contrasting those completely random zero-order letters with second-order word approximations, where the choice of the next word heavily depends on the frequencies of words following each other, we start to clearly see these underlying statistical structures. Language is constrained. The letter Q is almost always going to be followed by U. The word V is highly likely to be followed by a noun. It's not random. And we can actually see how this builds up mathematically using Markov processes. These map out how the probability of a letter or word choice entirely depends on the states of the preceding letters. You can think of each junction as a state, and the arrows represent the mathematical probability of moving to the next specific letter. What Shannon realized here is absolutely crucial. If we know these probabilities, we can vastly compress the data we're trying to send over our communication channel. Which perfectly sets up section 4, entropy and message redundancy, where we really focus on measuring all this uncertainty.
Shannon borrows this concept of entropy straight out of statistical mechanics. Now in physics, entropy measures disorder. But in information theory, Shannon uses it to measure the amount of information generated by a source per symbol. And that basically equates to how much choice or uncertainty is involved. Think about it. If you know exactly what the next letter is going to be, the entropy is zero. There is absolutely no new information being delivered. Because of this incredibly measurable statistical structure we just looked at, Shannon ran the numbers and calculated that the redundancy of ordinary English is roughly 50%. So what does that actually mean for us? It means half of what we write is dictated entirely by the rules of the language itself, and only half is actually chosen freely by us. And here's a super fun fact from the source material. It is this exact 50% redundancy that makes large, two-dimensional crossword puzzles mathematically possible in the first place. No way, right? If the redundancy was zero, literally any random string of letters would be a valid word. But if it was much higher, the language would be way too constrained to ever allow words to intersect cleanly on a grid. It's the perfect sweet spot.
All right, we've made it to our final section, Section 5, Combating Channel Noise. Now it is time to deal with the ultimate villain in all of communication. See, when noise corrupts a signal, we can't just subtract the number of errors to find out how much information got through. Why not? Well, because the receiver literally doesn't know where the errors occurred. Instead, we have to use equivocation. This lets us mathematically measure the exact amount of missing information that got stripped away by the noise. Basically, it measures the average ambiguity of that received signal. So, how do we defeat this noise? Shannon introduces an observer and a correction channel, and he proves mathematically that if an auxiliary correction channel's capacity matches the equivocation, that missing information we were just talking about, you could encode data in a way that allows the receiver to correct almost every single error caused by noise. I mean, this is it. This is the bedrock of how data is reliably transmitted across the globe today without degradation. We're talking everything from deep space probes to the smartphones sitting right in your pocket. It all comes back to this exact math.
And that really brings us full circle, doesn't it? Shannon brilliantly stripped away meaning to solve the engineering problem of how to move information perfectly from point A to point B. But it leaves us with something pretty profound to wonder about. If we can mathematically guarantee that a message arrives perfectly, completely regardless of its meaning, where exactly does the engineering of information end and human comprehension begin? Thanks for joining me on this explainer. Keep learning, and I'll catch you in the next one.